I would like to take the derivative of the function e to the negative x times sine of x. So this could be pretty useful in certain applications of math, and I would really like to be able to take the derivative. Instead of taking the derivative just like it is as a product of two functions, since that's e to the negative x, I'm going to move that down into the denominator as e to the x. So I want the derivative of sine of x over e to the x. And I could use the definition of derivative to try to figure this out, and I may get somewhere with it, but it would probably be messy, and I may not even be able to get anywhere with it. So instead of doing that, I'm going to try to figure out a pattern for a general quotient of two functions. So I want the derivative of f of x over g of x, where f and g can be any two functions. My guess is that this will give us just the derivative of f over the derivative of g. That's what I'm expecting. So I'll test that on a really simple pair of functions. Let's say I want to take the derivative of x cubed over x. So f is x cubed, g is x. Then if I'm right, that should give me the derivative of x cubed over the derivative of x. So that would be 3x squared over 1, and that's just equal to 3x squared. Now, we can also calculate the derivative a different way where we actually know for sure how to take that derivative. X cubed over x is x squared. The derivative of x squared is 2x. So my guess is way off. We're going to have to figure out something else to do with this. So maybe there's a pattern that we can use, maybe there's not, but let's use the definition of derivative to see if we can figure out a pattern. The derivative of f over g is the limit as delta x goes to 0 of, and then I need y2 minus y1 over the change in x. So my y2 here is going to be f of x plus delta x over g of x plus delta x. And then my y1 is just f over g. There's really not much I can do with it from here if I keep it like that. So I'm going to change my perspective. I'm going to change the f of x plus delta x to focus on the change in y values instead of the change in x values. So I'm going to rewrite it as f of x plus the change in f. So that's like the original y value plus the change in y values when I let the x move a little bit. And then I'll do the same thing with the g's. And now I'm going to combine the two fractions in the numerator. And just for writing this out, I'll pull out the over delta x. I'll rewrite that as 1 over delta x times the rest of this stuff. My common denominator, notice, is going to be g times g plus delta x. So I combine those two fractions. Then I'll simplify the numerator, multiply everything out, combine like terms, simplify it. And once I have that simplified, I'm going to bring that 1 over delta x back in, and I'm only going to multiply it into the numerator. So I have a choice of how to multiply it in. 1 over delta x times a fraction. I could just multiply straight across and bring the delta x into the bottom. But I know from messing with this on my own beforehand that that's not going to get me where I want to go. It's going to cause me to spin my wheels and not get anywhere. So I'm going to bring that delta x into the numerator as a 1 over delta x. So I'll multiply that through the numerator. And then I'll rearrange those numerators so that it looks like this. And now when I do this, I see that I have some nice things that will pop out of this. I'm getting g times this limit, and notice that limit is just f prime of x. So I get g times f prime of x minus, and look, this is f times g prime of x. And then in the denominator, I'm getting one piece that's just going to leave me with g squared when delta x goes to 0. And then the other piece, look, notice what happens to it. Remember, at the beginning of this, I'm assuming that I can find the derivative of f and g. So f and g must be continuous. In particular, that means if delta x shrinks down to 0, then the change in g also has to shrink down to 0. So for this other term, when I let delta x go to 0, that whole term turns into 0 times something, so that whole term goes away. So I'm just left with this g times f prime minus f times g prime over g squared. I would have never guessed that pattern, but it looks like that's the pattern that I can use from now on if I just memorize it. If I don't memorize it, then I'll just have to use the definition of derivative every time I want to take the derivative of one function divided by another function. So I'm going to go ahead and try to memorize this, even though it's slightly complicated. But let's go back to our original simple example and test this pattern and see if it really works with that one. So here my f on top is x cubed, my g is just x. So according to my pattern, I should have x times the derivative of x cubed minus x cubed times the derivative of x divided by x squared. So if I do that and I simplify the numerator and combine, and then I just divide by the denominator, then you see that what we get there is just 2x, and that is the derivative of the original function. X cubed over x is x squared. We know the derivative of that is 2x. So this pattern really works. It's called the quotient rule, and it can save us time.